The past week in science offered a powerful reminder of how much the universe, and even our own planet, remains unexplored and quietly mysterious. Among the most striking developments were new findings about Comet 3I/Atlas, an object that does not merely belong to our solar system, but appears to have wandered into it from the vast stellar wilderness beyond. First detected in late June, the comet immediately drew attention because of its unusual trajectory and behavior, marking it as an interstellar visitor rather than a native body bound to the sun. Over the following months, astronomers across the world began piecing together its story, and recent analyses suggest that this object may be far older than initially imagined. Based on its velocity, composition, and orbital characteristics, scientists now believe 3I/Atlas likely formed in the outermost regions of the Milky Way, potentially during the galaxy's earliest formative stages. If this interpretation holds, the comet could be billions of years older than our Sun itself, preserving physical conditions that existed long before the solar system took shape. What makes this discovery especially compelling is that comets are often described as frozen time capsules, carrying pristine material from the era in which they formed. In the case of an interstellar comet, that concept is taken to an entirely new level. Instead of recording the early history of our own planetary neighborhood, 3I/Atlas may be offering a glimpse into a completely different stellar environment, one shaped by ancient stars and long-extinct planetary systems. Astronomers estimate that it may have drifted through interstellar space for eons, surviving radiation, gravitational encounters, and the cold vacuum between stars before its chance encounter with our Sun. That it remained intact for so long already speaks to its unusual physical resilience, raising questions about how common such ancient wanderers might be throughout the galaxy. Observations of the comet's behavior have only deepened the mystery. Long before it approached close enough to the Sun for solar heating to be expected, astronomers detected intense jets of water vapor erupting from its surface. One researcher famously described the outflow as resembling a fire hose, a level of activity that defies conventional models of cometary physics. Typically, water ice sublimates and escapes only when a comet nears the inner solar system, where sunlight becomes strong enough to heat its surface. In the case of 3I/Atlas, however, this activity was observed at a distance where such processes should be minimal. This suggests that the comet's internal structure, composition, or thermal history may be fundamentally different from comets formed around our Sun. Some scientists speculate that volatile compounds trapped deep within the comet may be releasing energy in unexpected ways, while others propose that its long exposure to cosmic radiation altered its chemistry over billions of years. The international scientific community has mobilized quickly to take advantage of this rare opportunity. Ground-based telescopes continue to track the comet's brightness and trajectory, while space-based instruments provide clearer views unhampered by Earth's atmosphere. In a particularly ambitious effort, the European Space Agency redirected one of its Mars-orbiting spacecraft to observe the comet as it passed through a favorable viewing geometry. This maneuver allowed scientists to capture the closest images yet of the comet's coma, the glowing cloud of gas and dust surrounding its nucleus. These observations are expected to yield crucial data about particle size, chemical makeup, and the mechanisms driving its unexpected activity. Every new measurement adds another piece to a puzzle that challenges long-held assumptions about how small bodies form and evolve in different parts of the galaxy. For while the drama unfolding in deep space captured headlines, an equally intriguing mystery closer to home resurfaced through careful reanalysis of old data. Scientists studying Earth's gravitational field have identified a massive gravity anomaly that appeared in 2007, stretching across a region comparable in length to the entire continent of Africa. This anomaly coincided with a phenomenon known as a geomagnetic jerk, a sudden change in the rate at which Earth's magnetic field evolves. At the time, neither event was fully understood, and remarkably, the gravity anomaly went unnoticed for nearly 2 decades despite being recorded by satellites specifically designed to monitor Earth gravity. Only recently did researchers uncover its signature while revisiting archived datasets with improved analytical techniques. The signal itself persisted for roughly 2 years before fading, leaving behind a tantalizing question: what could cause such a vast, temporary redistribution of mass within the planet? Current hypotheses point toward a previously unknown process occurring deep within Earth's interior, near the boundary between the mantle and the core. This region, inaccessible to direct observation, plays a crucial role in driving plate tectonics, volcanic activity, and the geodynamo responsible for Earth's magnetic field. Scientists believe that a rapid movement of dense material within the deep mantle may have altered the planet's gravitational field just enough to be detected from space. If true, this would represent a new category of large-scale geological behavior, one that operates on timescales and depths that have so far remained hidden from conventional study. The connection between the gravity anomaly and the geomagnetic jerk is particularly intriguing. Earth's magnetic field is generated by the motion of molten iron within the outer core, and changes in flow patterns can produce sudden shifts in magnetic behavior. If a deep mantle mass redistribution influenced heat flow at the core mantle boundary, it could plausibly trigger both gravitational and magnetic effects simultaneously. This possibility suggests a tighter coupling between Earth's internal layers than previously recognized, hinting at dynamic interactions that ripple upward from thousands of kilometers below the surface. Understanding these interactions is not merely an academic exercise. Earth's magnetic field shields the planet from harmful solar radiation, and subtle changes in its behavior can have real-world consequences for satellites, power grids, and communication systems. What makes this discovery especially humbling is the realization that such a massive event could unfold unnoticed for nearly 20 years. Despite an armada of satellites continuously monitoring our planet, the complexity of the data and the subtlety of the signal allowed it to remain hidden in plain sight. This underscores the importance of revisiting existing datasets as analytical tools improve, as well as the value of interdisciplinary research that connects geophysics, magnetism, and planetary science. Just as the study of an interstellar comet forces astronomers to rethink the boundaries of the solar system, the revelation of this gravity anomaly challenges geoscientists to reconsider how dynamic and interconnected Earth's interior truly is. Together, these stories form a striking thematic parallel. In one case, a relic from the earliest days of the galaxy drifts into our cosmic neighborhood, offering a fleeting chance to study conditions that predate the sun. In the other, a hidden process deep within our own planet briefly reshapes its gravitational and magnetic signatures, only to be recognized years later through patient scientific detective work. Both remind us that discovery is often less about finding something entirely new and more about learning how to see what was always there, waiting for the right question, the right instrument, or the right moment. As researchers continue to track Comet 3 I/Atlas and probe the depths of Earth's interior, they reaffirm a central truth of science. The universe, from the smallest planetary details to the vast spaces between stars, is far more active, ancient, and surprising than it first appears.